and welcome back to Aerospace and Mechanical Engineering Lab 2. Today we are going to learn how to create a CAD model of a traffic light beam and how to mesh it in order to simulate the fluid flow around it and do a structural analysis later on it. Okay. There are a couple of things that you have to know before starting this process. The first thing is for the next three labs, so this lab and the computational fluid dynamics lab and the computational mechanics lab, you are not going to write separate lab reports for them. You just have to essentially use whatever you do here in computational fluid dynamics lab and take the results of the computational fluid dynamics lab to computational mechanics lab and write a lab report. I will also send an email announcement about this so everyone is on board. And the final lab report you submit is essentially a mini project worth 15 points. So we have combined all of these three lab reports. We just have to submit that all of the lab reports together. You don't really need to write more than whatever you wrote for your other lab report. The material here is a little more, so you essentially have to write more, but the guidelines, the rubric and everything is very similar or is the same as the other lab reports. Okay, so computational fluid dynamics, computational mechanics, the first thing they do require is to create a CAD model, and the software you want to use is the ANSYS workbench. To open the ANSYS workbench on any of the computers in the computer labs, you just have to search for workbench and open the workbench. This is Workbench 2025 that I've installed on my own laptop. But in the lab, we might have Workbench 2021, 2019, doesn't really matter. They are essentially the same software and they haven't changed that much. When you open the Workbench, what's gonna happen is you're gonna see this window. This window, we have a lot of toolboxes here, essentially modules, a lot of analysis systems, component systems, and customs systems, design explorations, and a CT. We are going to use the analysis system. The analysis system combines a couple of different modules together and gives you a full analysis system. Yeah, so to do a CFD model or computational fluid dynamics simulation and computational mechanics analysis, we need to create a CAD model. That was the first thing. And the second thing is that we need to break that huge geometry that you have created into a smaller cells, essentially. And there's a mathematical reason behind this. We don't really need to get into the mathematics behind why do we do this, but the idea is we are going to learn how to create a CAD model using ANSYS and how to mesh it using ANSYS. Again, to create a CAD model, you can come to component systems and choose this geometry, drag and drop it into your workbench, essentially. You see this geometry here. If you right click on the geometry, it gives you a couple of options. One is a design modeler, another one is a space glim. They introduced another software, another CAD software that is not included in their 2025 version. So you might actually see three software here. The software we want to use is Design Modeler. Design Modeler is the oldest CAD model that was incorporated in ANSYS, and it does the job fine. Okay, so right click and then open the Design Modeler. If this is your first time opening this, it will ask you to allow administrative access and whatnot. On a lab computer, you can't do this. You just have to cancel. On your personal computer, you can allow this. And one thing to keep in mind is that I'm using the student version of the ANSYS, the student version. You can install the student version for free on your home computer or your laptop. You don't need to install the full version, have the full version. And the student version is free. Just Google ANSYS student version download and it will direct you to the appropriate website to download the student version. So this is the environment of the design modeler. And again, our goal is to create a beam, a traffic light beam. So essentially we want to create two cylinders that are perpendicular to each other. So there are a couple of different things we can do. We can go to this sketching right here. It lets us create a line or a polygon, rectangle, a lot of different things. But since our geometry is a very simple geometry, we can also go to pre-made geometries, primitive geometries essentially here. Right? They have a cylinder in their primitive geometries. And when you create a cylinder, you see it does show us the outline of the cylinder we have created. You just have to define the origin of the cylinder coordinates. We say it starts from 0, 0, 0, and then you have to define on which axis it is going to have its height, right? Right now it says x-axis component is 0, so it doesn't increase any height in the 0 direction. Y-axis component is 0, it doesn't really increase the height in the y direction as well. Z-axis component is 1 meter, and the radius is also 1 meter. 1 meter radius for a traffic light beam is a little too much. We want to reduce this to 30 centimeters or 0.3 meters. Okay. And the height of it, 1 meter is too small. 1 meter is, if you're not familiar with the metric system, is 3 and 3.4 feet essentially. That's a cell. Either too low. We want to increase this to, I guess 8 meters should be fine. The direction doesn't really matter at this point. If you are moving in the z direction, you just have to be cognizant of the fact that you have moved in the z direction. So this is the direction of my height. This is essentially xy plane is my ground, and this is coming out of the ground. And we are ready to create the cylinder. I'm going to hit generate right here on top, and the cylinder will be created. And you have to keep in mind that later on we are going to do a union operation or subtraction operation. And for subtraction operations, you want to make sure that you add frozen. The operation is to add frozen, not add material. So we can subtract this later on from a control volume. Okay, so we have the standing part of the beam. I want to add a component that is going to have the traffic lights hanged on it. Okay. Essentially, we need to create another cylinder. Cylinder again. It did create a cylinder on the same spot, but we don't want the origin to be at 0, 0, and 0 anymore. It has to be at 0, 0, and 10 because we want it to be perpendicular to the top of our beam. I'm sorry, 0, 0, and 8. I think we did 8 meters. Yep. Something like this. Okay. And then we want it to be perpendicular to our initial beam. So it has to be either in the y direction or in the x direction. Again, doesn't really matter which direction you choose. I'm going to choose the y direction. 8 meters beam again. See, so we have two beams that are perpendicular to each other. I'm going to change this 8 to 7.5 so the beams are completely flush. Yeah, exactly like this. 8 meters, everything else is correct except for the frozen. So we want to hit generate. We want to add these two beams together to create one single beam. So I'm going to go to create and then Boolean, start a Boolean operation here. A Boolean operation is a unite operation, but we have other types. We have subtraction, we have intersection, we have imprint, and so on and so forth. So for the unite operation, we have to select two tool bodies. You have to select both of them by holding the control button and then come to this yellow bar, hit apply. So the two bodies are selected and then hit generate. As you can see, we have one solid body. This is our traffic light. Well, our first goal in the lab, in this lab or in the next lab, is to simulate the fluid flow around this traffic light. Now, that is our first goal. So right now, we only have created the traffic light. We have to create a control volume around that, so we can tell a software later on that there is air moving inside this control volume and around this structure. So this has to have a box enclose it, essentially a control volume enclose it. And creating that box is also not that difficult. Again, you come to create. This can be a primitive shape. Go to box, simply. Just tells you where the origin should be. I want to start from, let's start from, we don't really need to, we need this to enclose the traffic light completely. So we can start of the coordinates, start of a coordinate system at x minus 5 and y minus 5. Okay. This part of the beam is just ground, so we are going to treat it as ground. The box doesn't really need to go deep in the z direction. And then we have 8 meters of beam and the 5 meters between the coordinates, the axis, the starting point of the box and the center of the coordinate system. So that's at least 13 meters has to be in the x direction, 13 meters in the y direction. But we are going to increase it to 20, so we have a good enclosure. And for the z direction, it is 1 meter. We want to go, let's do 13, so there is enough space for the air to move around. So this is how it's going to be. We are going to have flow coming in from this location, and then it will interact with the beam, and the rest of these boundaries are going to be outlets. So air is going to go out of it. I'm going to hit generate again. This also needs to be at frozen. So we have two bodies right now. What I'm going to do is I'm going to subtract the beam out of the enclosure. The reason is I want to analyze the fluid flow around the beam. That is the next step. The third step, we are going to come back to the beam and just focus on the beam itself. That's the computational mechanics lab. But for the computational fluid dynamics lab, which is the lab you're going to do after this lab, we are only focusing on the air around the beam. So we have to subtract the beam from this enclosure because the beam itself is not a focus for us. We are not doing a stress strain analysis. So we have to create, we have to do another Boolean operation. This time, this Boolean operation needs to be a subtraction. So our target body is the enclosure. I'm going to select it right here. And my tool body is the beam. I can see the beam from right here. I'm just going to select it. You see this right now, right here, it tells me that we have two bodies. At the point that I've selected, I'm going to select the second body, which is my beam. And it asks me whether I want to preserve the tool body or not. We don't need to preserve the tool body. So I'm just going to hit generate. And you have an enclosure, control volume, with the traffic light beam cut out of it. We are ready to go to meshing. So I'm just going to simply close this. And then add a meshing module. You see the meshing module is right here. I'm just going to drag and drop it on the geometry so it uses the geometry. And then we only have one meshing software here. There are other meshing softwares included. One is EMCH that I can't seem to find. But this meshing software, this is the built-in ANSYS meshing software, and it will do the job fine for us. Again, if you don't know what meshing is, we are essentially just dividing our geometry into a smaller cell size, and then we solve the problem in each cell independently and then connect all of the solutions together. I mean, the solutions of each cell feed into the next cell and so on and so forth. So double click on the meshing and just have to give it a minute to open up. I'm doing this on my laptop. It's not a workstation, so it's a bit slower than your regular workstation. And since we are using the student's version of the software, we are limited to 1 million cells, which is more than enough for our case. So you see a couple of different options here. There are a lot of different options, but we want to focus on the outline specifically. In the outline, it gives us the mother, and it does recognize that we have imported the geometry. Geometry is imported correctly. It is a solid, and later on we can change this to fluid because this idea is this is a control volume, and we are analyzing a control volume, a fluid flow in a control volume. And then we can set the material. The material has to be air. Then setting these things here is not going to cause any issues or problems later on. We can always change this later on in our other the other software that we are using. You see the beam cutout and the coordinate systems. We have the global coordinate system. The last one is meshing. So when you click on the mesh, it gives you a lot of options right here. Essentially, it is telling us how we want to display the mesh and so on and so forth. Physical preferences. We want to do computational fluid dynamics, so we can change this to CFD. Again, you don't have to make these changes, but we can. And we can choose the largest element size. The largest element size, which is essentially the size of those cells, the width or length of those cells, is 1.5 meters. This is a little too big for a simulation case that is 10 meters total. So we want to make sure that this is small. Let's change this to, I guess the maximum cell size we want to get can be 50 centimeters for a rough simulation. But if you want to have a good simulation, you want to make sure that this is even smaller than this. And then we don't really need to change the export format, and we also don't need to change the surface mesh. The sizing part goes into sizing with a little more detail. It starts usually with a very smaller cell size, and then there's a growth rate, and the software automatically chooses where it needs to apply the smallest cell size, which is usually around the beam, right? And a lot of sizing options. You can actually set the settings for inflation, quality, and there are advanced settings. You can set the number of CPUs that are going to be used in creating this mesh. We are not using a very computationally expensive model, so we don't really need to choose these. We can also change the type of mesh. Do we want to have a cubic mesh or a triangular mesh? And we're going to talk about that later on. And here it tells you how many data points you have. Right now we have none because we haven't meshed this yet. But if you right click on the mesh, you're going to see that there's an insert option. This insert gives you a lot more options. Right now, I'm going to insert the method. And this method, I'm going to make sure that I choose my geometry first of all, and then select it, apply it here. This method tells us how we want to mesh the system. Is it, again, quadratic, triangular, hexagonal, different types of mesh. This is not a very structured geometry, so we shouldn't really use a square mesh. what I'm going to do is I'm going to use tetrahedrons. Very essentially similar to triangular meshes. Yeah. Do we need to change the other options? Not really. You can just let it be. And then I want to make sure that my mesh around the beam is very fine. So what I'm going to do is I'm going to come back to this mesh, right click, click on insert, and click on the sizing. Okay. And then it is asking me to choose where I want to set the sizing. I want to have a set number of data points on the beam. First of all, this is a surface that I'm looking at, so I have to change this selection from body to surface, to face. Right? And when I click on this, it gives me the option to select this one of the beams, and then this other one was somewhere here. So I'm going to hit the control button. So it chose the wrong surface for me, but I can change the selection using these options, right? This is my selection. So right now, I also want to deselect this. Yep. Right now we have selected our beam. Okay. I'm going to hit apply. And the only thing I really want to set here is the element size. It says by default, it should be 0.5 meters, so 50 centimeters, 1 feet and 1/3 of a feet, which is too large for us. So I'm going to change this to 10 centimeters. So what's going to happen is we are going to have the smallest cell sizes around the beam, which is going to make our simulation more accurate. It might make it more unstable as well, but it will definitely make it more accurate, and most probably it will make it more accurate. Okay. And we are ready to make the mesh. I don't really see any other issues. There are other options there are other things you can do in the meshing software here. You can create a refinement zone if you want to. There are different types of things that you can do with your mesh, but for the purposes of this lab, just a face sizing and a method selection should be more than enough. So I'm going to hit generate right here, and we'll start creating the mesh for me. Okay, it did create a mesh very fast. We can actually check the mesh by coming to the statistics. We have 59,543 nodes, so essentially points, and we have 320,000 elements. So we are well below the limit for the free software. So the mesh is ready. The only other thing that needs to be done is to name all of the faces. Essentially, we are creating the boundary conditions. If you recall from your partial differential differential equations course, to solve a partial differential equations, we need to have boundary conditions. These faces, or these boundaries that we are going to name, are going to act as those boundary conditions that we need to solve our problem. How do we name all of these faces? Just have to click on the face. First of all, you have to go to face selection. Click on the face. For example, this one, we already know that this is the inlet of us. This is where the air comes in. I'm going to right click on the face while it is selected and create a name selection. Just call it inlets. Okay. And then this is the ground. So I'm just going to select it, name selection. I'm going to call it wall or wall 1. Because the ground essentially is acting like a wall as far as the fluid flow is concerned. There is no slip condition that is applied here. We're going to talk about all of those conditions for the next lecture. And then this one is the outlet. I'm going to call this outlet left. I'm going to call this one outlet top. I'm going to call this one outlet back. Let me check which wall is not selected. So this one is named. Then the only thing that is left is this one, which is our outlet right. You want to make sure you name all of the surfaces. So the last surface that is left is the traffic light. And I'm going to select this traffic light. Again, I'm going to select both of them together. The traffic light is selected. Right click on it. And I'm going to call it wall traffic lights. Okay. So as you can see, all of the boundaries are named. The mesh is created. We are ready for the simulation. So essentially for your submission to Blackboard, the only thing you really need to submit, and it says you are graded for this is worth five points, but you just have to make sure you submit this. And it is not worth 5 points. All of your report together at the end of the third lab will be worth 15 points. So this submission is just something you need to do. And if you don't do this, then you won't be able to move on to the next step and the next steps and the next step. You want to make sure that you just save this file and submit it to Blackboard. Okay, so this is it for today. You want to close this. You want to make sure there is a check mark. And then you want to save this. I'm going to save this as on my desktop as numerical lab 6 numerical model. So I can come back to this to use the geometry I've created in lab 7. That is it for today. Thank you for joining us and enjoy the rest of your day.